Okay, no questions? There's not any questions? Can't regress? Okay. So we were talking about microelectronics bonding, and I guess I put up this figure, and I don't think I passed around too many things yet. We basically showed the number of inputs and outputs as a function of time in different types of packages. To show you some of the types of packages, this is what's called a pin grid array. This is kind of 1980s technology. And again, it's a multi-layer ceramic. It's got tungsten inside. You use tungsten with the aluminum oxide because they have the same coefficient of thermal expansion. If you heated them up to 1200 degrees centigrade, which is typical firing temperature for something like this, and they didn't have the same coefficient of expansion, they just tear themselves apart as they cool back down. Okay, so they have to have a pretty good match. And you have these pins, and you should just, you looked at a 286 computer in the 1980s, this is probably what they would have had the PC chip on. The chip would be on the inside here. This is all gold plated afterwards. The connection points, you can count the IOs. This thing probably has, looks like 60 or 70 inputs and output connection points. Actually, you can count them out here because it should be the same number out there. And they actually put two rows of pins around there. It's perimeter bonding, and it's a mechanical connection. Compared to other technologies, that uses an awful lot of real estate, but it's still better than the dip. I passed this one around yesterday, right? I think so. I passed some of these around, the tap bonding and stuff. This one, the only reason I keep it in the plastic is because it's so small. This is what's called the ball grid array or flip chip. With various versions over here, flip chip, chip scale packaging. This is the one that was invented in the 1960s by IBM, but really was way ahead of its time. The chip goes on this side. There's a bunch of little wire bonds. I'm sorry, not wire. Yeah, there'd be wire bonds to go to the chip on this side, and this side is actually an area bond. Okay, there's a bunch of little gold dots around here, a whole series of them. And you make little solder balls on each one of those. I guess I could show you. Ball grid array bonding. Okay, so you have this will be your silicon chip, and it will have some little solder balls on them, and you're going to bond to some substrate, one of these things. They'll have little solder pads on it, and so you put your chip on here. And put it to you can put it directly to your printed circuit boards as far as that goes. In fact, that was something they talk about real estate on a printed circuit board. Okay, and real estate is important. You know, the more densely you can pack your components, the smaller your electronic package can be. And if you're trying to make a cell phone or something like that, or a iPod, and you try to make things nice and thin, or actually make a laptop computer, you want to pack things as tightly as possible. The other reason you want to pack them as tightly as possible is the reason I had on the end of the board yesterday. If you start working at 3 gigahertz, then you can't go more than 4 inches at the speed of light at that frequency. Okay, remember it's 3 times 10 to the 9th divided by 3 times 10 to the 8th or whatever, or the reverse of that. And it gives you a tenth of a meter. A tenth of a meter is 4 inches. So even if electrons travel at the speed of light, you can't do your computation or whatever you're trying to do more than 4 inches away, because of capacitance losses. You slow down the electrons below the speed of light. If they're only going half the speed of light, everything has to be within 2 inches. And that's one of the reasons the Defense Department was trying to create 2-inch chips, because they could get to those types of frequencies. If they actually had to go from one chip to another, it might take 3 inches to go that distance, and you get higher speed. We're getting to the limit of how tightly we can pack these things. Well, ball grid array allows us, it was way ahead of its time when IBM started it, but here's a cross section of it, if you will. And you have to worry about coefficients of thermal expansion. But you have these little solder balls. Here's your integrated circuit. Here's your substrate. Your substrate is going to have layers and layers of the same tungsten and aluminum oxide. The problem is this thing heats up. If it's running at 30 watts per square centimeter, remember each chip's about a square centimeter, and your pentiums now are running at about 30 watts. And some of the fancier ones might be running at 70 watts. If you get to those types of heat intensities, that's the same as a propane torch. And this thing's going to expand. This thing's got a different coefficient of expansion, and you've got a problem because this thing will just tear itself apart. You know, in shear, as this thing expands less than this one expands more, and the grids balls out here on the edges are going to have more strain than the ones in the center. And so, in fact, it turns out we've got perimeter bonding, which is things like the tab bonding, and we talked about that yesterday. And you might get 400 IOs. But if you are getting to the point where you want 800 IOs for twice as many, or not twice as many, but about 5 times as many, so maybe this is 10 to the 7th transistors, but if I wanted to do 10 times as many transistors, which is what we're getting to now, 10 to the 8th transistors, I probably need 1,000 IOs or something like that, input and outputs. Well, one of the things people did, particularly with those little wire bonds, they would do a double, one set of wires over the other. If I look at the cross section, I might have a wire coming out here to a pad, and then I could have another wire coming out to another pad, right? Just a little taller wire. Well, now I got to make, you know, instead of 800 of those thermocompression welds, I got to make 1,600. And I've got to bring my little machine in and do it on top of ones. If anything gets out of registry, I'm going to knock one of them apart that's underneath. And anyway, so people have done that, but that's still perimeter bonding. Area bonding, if you have these little ball grid arrays, you can easily get, in theory, up to about 2,000 inputs and outputs on your chip. So perimeter bonding is typically limited to about 400. Area bonding with ball grid array, you can get up to about 2,000. Beyond that, it's not clear what we're going to do or if we need to do anything. Because frankly, Rent's rule basically said as you put more and more chips on there, you have more and more functions on your chip, and you just keep on needing to have more inputs and outputs. However, there's a theory, some people say that Rent's rule is going to bend over, because once you start integrating more and more onto the chip, it used to be in the old days, the 2nd generation Pentium had a chip like this and a chip like this, and I mentioned that's what we call dual for today. And this whole thing is on something that's only about 2 inches wide. So even though we've got small chips, I'm within my 3 gigahertz communication distance, okay? But what happens is if I end up with a single chip that's bigger, let me kind of do it scaled. Let's say I had a single chip that was 1 inch on a side. Well, and it's got, that's 6 times as many, 6 times the area of a 1 centimeter chip, because it's roughly 2.5 squared, right? So I got 6 times the area, but I also probably, as I go on to the next generation, may have another smaller line width and everything else. So I may have 10 times as many transistors on this one as I had on this one. But when I start doing that, maybe the number of IOs goes down because I've done all my integration on this. And I'm doing a lot of my work that I used to do outside the chip, I can actually do on the chip. And now we're talking about hybrid chips that basically integrate photo optics, you know, so you can do a little laser fiber optic communication on the same piece of silicon that you do your digital computation. Well, you don't need as many IOs because now your IOs they're not IOs, they're on the chip, communication on the chip. So hopefully, and people are already starting to design things as they get fancier and fancier to put in different types of circuits on the chip. Now a memory chip, it's the same circuit all over the whole thing. A microprocessor, you already have 4 or 5 different blocks. You know, you have a computational block, you have a memory block on there, and you have a little controller block that basically helps time and keep everybody marching together. Okay, there's different little modules. So the modules that used to be individual chips are all going on one chip, and so Rent's rule about the increasing number of IOs as the number of transistors increases is probably going to break down and start the curve and start bending over. The curve being this curve. Okay, this is sort of Rent's rule. Okay, and the question is, does this essentially, once we get to enough transistors on a chip and we start doing more things on the chip, after all, if I had everything on a chip, then I might only have 10 or 20 IOs, right? For some of these things. I mean, what does the radio need, or whatever it is I'm doing? How many inputs and outputs? Okay. But there's always a proliferation of inputs and outputs also until people standardize. Anybody have a high definition flat panel TV? Okay. How many inputs and outputs you got in the back of those things now? I mean, I hardly have room in the back of one of those great big screens. I mean, I got one at Christmas time when I got my son an Xbox 360 for Christmas, and then I decided, well, you know, so I got it and I looked behind that thing. I thought, there's got to be 50 or 60 IOs back there, right? For all the different types of inputs and outputs that are back there now.
So you get $100 cable, DVI inputs.
You go to get a DVD player now, and the whole back of the DVD player is nothing but IOs. I mean, you know, it used to be there'd be 4 or 5 or 6 or something. Now there's 20 or 30. You got to get back to the point where only a teenager will be able to hook it up. Okay, so the generational history of doing this started out with wire bonding, which we've talked about. And wire bonding started out in the 1960s, and it still progresses, and we still use it today. There's a company in Pennsylvania called Kulicke and Soffa, and they are kind of the world leaders in making these little sewing machines. But the problem they have is the spacing for perimeter bonding is about 7/1000ths of an inch. Okay, and therefore on a 1 centimeter chip, you can only get about 200 to 300 IOs. So if I have simpler chips, I can do this, and this is thermocompression bonding. They may heat things up to a couple hundred degrees on the gold wire. That just helps get some of the oils off. Gold doesn't have an oxide. You don't have to try to get rid of the oxide. But gold is a metal. It has a high surface tension, and so any oils, and there are always oils in the air. And in fact, one of the places that has the most oil in the air is something like the Great Smoky Mountains, because the trees give off oils. Okay, they aspirate, you know, organic molecules because they are organic. Okay, and basically, there's always oil in the air unless you're in some place that has no trees, like Arizona, or whoever the person was from Arizona. Didn't I have someone from Arizona? No, maybe my other class had someone from Arizona. I said something about Arizona. I said yay. Anyway, tab bonding, which is tape automated bonding. That's the thing I passed around on that little tape. Kind of came in the 1980s, later 80s, and it goes up to about 400 IOs because it has a spacing of about 4,000. Here, it's not the wire size on the wire bonding. It's the little sewing machine that has the head that has to come in and make the mechanical attachment. You're putting, you know, it's not a lot of force, you're talking grams, but even so, when you start getting down to things that are no stronger than a needle, when you start talking tens of grams, you start running into stiffness problems. And so about the closest, they have done 005, but in large scale production, they're kind of limited to 007. Tape automated bonding is perimeter bonding. This is perimeter. And then area bonding, which is, I'm just going to, well, I'll give it the IBM name, C4, which is controlled collapse chip connection. And that was actually the late 60s, and it really wasn't used, but it's area bonding, and well, who knows what the sizes are, but typically it might be a spacing, the smallest spacing. Sometimes the spacings are a millimeter, like that one I passed around, probably maybe a millimeter or a millimeter and a half. But they have gotten down to 10 mil ball sizes, but you're area bonding, so now you're up to, in theory, about 2,000 IOs. And we really haven't been able to go above that, but like I say, it's not clear if we really will need to go above that. Another item in packaging, electronic packaging, this is all sort of what they call level 1 packaging. There's actually a level 0 packaging, or level, this is interconnection. So if we're talking electronics, if we're talking interconnection technology, there's a level 0, and that's on the chip. And that means on a piece of silicon, I got to make a connection from one transistor to the next. And I do that by vapor depositing metal in one of those 200 steps where I'm putting all the dopants and thin film resist as I'm building up that silicon chip. On the silicon chip itself, I'm making connections between things, and they call that level 0. What I've just been talking about up there is level 1. Well, actually, they don't usually use Roman numerals, they usually use Arabic. So level 1, and that's chip to package. Remember, the packages are these tungsten aluminum oxide composite structures. And then level 2 is package to board. So I've got a motherboard on my computer. Okay? I've got to take this packaged semiconductor and I've got to attach it to the board. And level 3, we'll talk about that in a second. Level 3 is board to board. And board to board, basically, I've got subboards. You know, I got a PC card that I want to slip into my computer. I got to connect that to the motherboard. And so there's these little clip-in slots. I mean, if you look at a CD card or an SD card, you know, a little memory card, they got connections. Those connections would be a level 3 interconnect, and a level 4 interconnect is a system. And that's basically where, if I got a rack of electronics, and each component, you know, I got a radio, and I got a sonar, and I got a whatever it is, and they all go into this rack, that type of packaging is level 4, the interconnection between those components. Okay? So system-wide components. So there's really, I don't know of any one company that does all of this. This is basically your Intels and Advanced Micro Devices and Delcos. Anybody know why I mentioned Delco Electronics? Delco Electronics, which used to be part of General Motors, now spun off, makes more semiconductor chips than anybody else in the country, and that includes Intel. Okay? There are like 50 chips in the average car now. Okay? They make a lot of cars. They're a captive for what's called foundry for the automotive business, but they make more semiconductor chips than anybody else in the world. Okay, a lot of people don't realize that because it says Intel on the computer, but when you buy a car, it doesn't say Delco inside, but Delco's in there. Okay, so anyway, this is the people making the chip. Chip to package is also Intel and others, but it can also be people who are making printed circuit board, because one of the things people have been doing is integrating these two with what they call, over the last 10 years, started about 10 years ago, chip on board. And it really started, the cell phone business started a lot of this. You didn't have a lot of room. You wanted to get these things smaller. I should have kept my old original cell phone. It was the size of your water bottle there, right? And it had lousy reception and everything. Anyway, so they just basically put the chip not into a package. They skipped the package. That stupid package cost $50. If you can put it directly on the printed circuit board, on this thing, put the chip directly on it, and then encapsulate it, you've done your packaging at the same time. You've skipped the whole level. And in fact, that's what they've done in miniaturization of laptop computers, cell phones. They basically do chip on board. In fact, that's why Intel would do this. Intel would do the interleaved bonds to the Pentium, and if you wanted to put the Pentium directly on your printed circuit board, they would sell you this and package it like this, and you would do the outer lead bonds directly on your printed circuit board. And then you would cover it with plastic for encapsulation to protect it. Okay, yeah.
Curiosity, just when you go to some of the Asian countries, a lot of electronics they have over there are so much smaller than we normally see or buy in the United States. Their radios and cell phones, stuff they wear like a necklaces. They're so small.
Yeah.
I was wondering if are they using processes that we don't use in America that maybe are better at packaging chips and that kind of thing?
Well, a lot of the processing is done over there. Okay, and so the problem is they tend to be first adopters of technology, and it's partly, well, in Japan it's part of the culture. I worked for the Office of Naval Research in the mid-'80s and lived in Tokyo, and I remember my son, who's now 32 years old, who was 10 years old at the time, and he wanted one of these radio-controlled cars. Well, they cost $150 back in 1985. That was a lot of money for Matthew when he was 10 or 11 years old. And he didn't want any, I can't remember how, he didn't want any presents for Christmas, and he wanted his birthday's in January. He didn't want any presents. He just wanted the cash from everybody because he was going to go out and buy himself one of these radio-controlled cars. Well, 10 years later, you could buy those things for $20, and I'm talking about the ones that are this size. And this past Christmas, as a stocking stuffer, Matthew gave me one that's this size that I think you can pay $10 and get one of these radio-controlled cars, right? And they're much smaller. Well, he was 10 or 11, and he saw them in Japan in 1984, and he wanted one. But the problem was they weren't selling them over here until 2 or 3 years later. So basically, because they were built over there, they were sort of first adopters. And the Japanese culture is not as bad about, well, it didn't work, I'm going to bring it back, okay, as the American culture, okay? So they're willing to accept, when they're getting cutting edge, toys, they're willing to accept more grief than the average American. So, and that's what I remember when I first went over to Japan in 1980. Everybody says, "Oh, can you buy me a camera?" And I went over there, and camera prices were higher over there than they were here. I could buy anything cheaper in the United States than I could in Japan. And in many cases, it was the same thing. In some cases, you're right, it was something new and different, like an MP3 player, and the Sony Walkman started out in Japan like 6 months before they really came over here. And the Japanese actually have a philosophy of try it out in Japan before they try it somewhere else. So they kind of beta test the consumers in Japan. And I can remember going out to Yokota Air Force Base to go shopping once a month or whatever, and you'd see all these C-5 cargo planes. like 10 of them typically parked there on a Saturday afternoon. And what had happened is these National Guardsmen from Seattle or Portland or whatever needed to get their flying time in. They would fly over to Yokota to get their flying time in. They would mostly be loaded, you'd see them offloading pallets and pallets of Coca-Cola. I could buy a case of Coca-Cola in Tokyo for $3 a case, and whereas in the United States I'd be paying 6 or 7, but that's because I didn't have to pay tax, and you get the military PX, type of prices. They would all, right across from the main gate at Yokota, you walk across the street, and there were about 10 huge electronics stores. So these guys would come over and buy the latest and greatest stereos and stuff, and then fly back. I figured each one of those flights only cost me, as a taxpayer, about $250,000, right, each weekend for these guys to get the flying time in. To bring cheap Coca-Cola to Japan and for these guys to be able to buy their stereos, right? But they got their flight time in, and then, every time I did that, my kids loved it because they could actually go to McDonald's and all the things they were used to, which you can actually get in Japan, but it was different on base. I mean, McDonald's is not exactly the same taste in Tokyo as it is at the base in Japan. In the base, it's the same taste as here in the United States. It may not be that good, but it's the same. Okay? Known quality. So, does that answer your question? I mean, they're kind of early adopters. And they're not, it's not that we don't know about the technology. A lot of that technology is stuff that we transferred over to them. Okay? Some of the stuff they developed, Matsushita, which is National or Panasonic brand, and Mitsubishi and Sony and stuff, they're developing some of their own, but a lot of it, Motorola developed the technology for the early cell phones, and originally was assembling them in Singapore or whatever. They ended up bringing them back to the United States in Boynton Beach, Florida, and this was kind of a big deal in the early 90s. And the reason was, first of all, they automated the line. So the line wasn't much bigger than about 5 of these classrooms to assemble the cell phones, but they could get them to the customer within 36 hours. From order through bill to ship was 36 hours. If they did it in Singapore, it was 2 weeks. Okay? And so it was the time to market. Actually, no, I'm sorry, it wasn't cell phones at that point, it was pagers. And there were so many different types of options, like frequencies and everything else on the pagers. You had to kind of, they were basically custom built, because you had a bunch of switches, like 10 different switches for all the different frequency and other options in there, that it was better to pay more in an automated line in Boynton Beach, Florida, and be able to get them to the customer for that extra bonus you could get in service of you order your pager in 1990 and you have it 3 days later. Now you just go to the store and they order it because they got a little chip in there that you can program all that stuff. But back in 1990, they actually had little mechanical switches in there that you had to set, okay? And that had to be done in the factory. And so the factory in Singapore was a problem. So there's all these kind of manufacturing constraints. Just a whole other subject. Okay, so you got all these board-to-board technology. A lot of this is, the biggest company in the world is AMP. We at MIT, we have the Whitaker College of Health Sciences and Technology. Well, Uncas Whitaker was the founder of AMP. He was an MIT grad. And AMP is a $2 billion company in Harrisburg, Pennsylvania. And all they make is these little plug-in connectors for boards to boards. And that's not all they make, but that's most of what they make, is that kind of, this type of technology, and all kinds of people buy this. And this is basically wires and cables and things like that. Actually, AMP makes these types of things. So there's various companies that make these different types of packages. An idea of, this is what's called a J-wing attachment. This is basically soldering, and we'll talk about soldering later, but this would be packaged to board. This would be a level 2 interconnect. So here's your aluminum oxide package, and somewhere up in here is you got your silicon chip bonded with the ball grid array or whatever. And this is a J-wing. This is just a little metal clip that comes out, and this is a solder pad. This has got all kinds of solder pads on it. So this is, packaged board. Here's the type of board it would go on. It can be a very small one. It can be flexible. Anybody has a 35 millimeter single lens reflex camera, and they give you information about how they manufacture them now. That whole thing's got a flexible circuit board. It kind of conforms to the shape of the camera. Because they got so many computers on there now, they probably got 10 chips inside there. But sometimes they'll do an explodable view, and they show you this kind of flexible printed circuit board, which just kind of drapes around the inside of the camera body, like putting an overcoat on somebody. Okay, and then they put the package, the plastic package on the outside to protect that. But so you may have that, maybe have chip on board technology because you're really trying to save space. But these are the type of J-wings, and here's a bad solder joint. And they have people who go in and repair these solder joints. Now there's an interesting story about one of the Motorola facilities. It might have been Boynton Beach, but it might have been another one, I can't remember. But for years and years, people knew that you always had to have 4% rework. If you were talking about kind of levels 2 and 3, you typically have 4% rework. And so the industrial engineers would design the factory when they have these automated things to solder the printed circuit boards and stuff. They would leave an area large enough to have people there with little soldering irons go in and fix these type of bad solder joints, and for 4% of the product. And one manager, as they were designing the plan, said, no, we're not going to have any rework area. And the engineer said, what do you mean? What are we going to do with the scrap? He says, we're going to throw it out. Well, you can't throw out a $200 pager, this was back when pagers cost a couple $100, just because, you know, you can't repair it. That's going to kill everything. And the engineers were just berserk, okay? This manager was not going to let them even design an area in the building for a rework. And what happened, this rule of thumb across the industry of 4% essentially evaporated in that plant. Because the engineers found they had to go back on the actual production line and solve the problems there. So they wouldn't have any rework. And that's the old thing in the early 90s. There was this thing, Duran was talking about 0 defects, okay? Well, 0 defects is a great goal, you can never get it, but you won't get it unless you shoot for it, okay? Was the lesson there. And Motorola broke the mold and said, we're not going to accept any defects, we're going to fix them, build it right the first time, and we're not going to have to do any rework. And they found that, no, the only reason they had 4% rejects was because that was the level they were willing to accept. And the reason they always got 4% rejects is because the engineers would always solve the problems on the original production line until the rework area could handle the rework capacity. And that was a self-fulfilling prophecy. My other example of that story, there's a Mustang plant for Ford in Detroit, and every now and then they'd fill up they'd assemble the car, and they'd put some gas in the tank, and they'd turn the key, and it wouldn't start. Ordinarily, at the end of the line, they turn the key, and the car would start, and the guy would drive it out to this huge parking lot where they're going to store the cars until the trucks and the railroad cars come by to, you know, take them away to the dealers. But every now and then, it might be one car out of 100 or whatever, the car wouldn't start. And so they had a little tow motor, you know, that would come in and it would hook up to the car and it would drag it out to the parking lot to a rework area. And then some mechanics would go in there and figure out why this engine wouldn't start when you put the key in. And one manager says, no, no more tow motors. If it doesn't start, you push it. And guess what? Within weeks, every one of them off the end of that line was starting. Because the employees didn't want to have to push it. So they made the engineers go back and make sure those engines started. Okay? So that's two examples of you get what you accept to a certain extent. That's not always true, but that's two examples of it. Okay? So this is a J-wing package because you can see the leads are like that. If you bend it out the other way, it's called a gull wing package, and a gull wing has that's a good gull wing, and these are other soldering type defects, so far as that goes, and that people spend their time repairing. Going back to the ball grid array, if these are my ball diameter and my pad, my pad might, that the solder ball's going to wet to, might look something like this. And this, the smallest that I remember is about 10 thousandths across here. Most of them are like 30 or 40 thousandths, okay, of an inch for get enough inputs and outputs. And you put a little ball on there. And this little book was talking about the size of the ball versus the size of the pad. Well, obviously, things are going to wet differently. You're going to get it's going to wet differently. But you can also, one of the advantages of control collapse chip connection is that when you put the chip onto the pads, if you misalign it a little bit, then it turns out to be self-aligning. Once that, so these are the little balls that are already on top of the silicon chip, and now you're going to connect them to the pad underneath. And you have these little copper solder pads, which may be pre-tinned with a little solder. You come in here and you heat the thing is warm, and you heat it up, and it starts to wet. As it wets, the thing will actually create a shear force, causing it to self-align. So one of the advantages, you can put that on there so the two are displaced this way, or they might be twisted with respect to one another. If it's only a small displacement, as long as those balls touch the pad, the surface tension actually brings it in nearly perfect alignment. So that's one of the advantages of ball grid array. And people are looking at different ball compositions. The solder here may be different than the solder of the ball. People look at, these things do heat up and the substrate expands, particularly if you're doing it directly chip on board. This is a polymer based printed circuit board, and it has a much higher coefficient of expansion than the silicon. And so I can't tell you about it. I had a student, bachelor student doing an internship at Motorola, and I had to sign a confidentiality because he found a particular type of solder geometry ball gave great fatigue properties in terms of thermal fatigue. How many times you could cycle this thing, heat it up and cool it down before you would actually tear some of the connections apart. Okay, they found something that had 100 times the life of the other design. So there's all kinds of ball grid array designs. Just to give you an idea, one book, and you don't have to worry about all of these, but everybody's got their little, okay, this is micro ball grid array, registered trademark. I don't even know who that is. But anyway, they've got, here's your silicon chip at the top of each one of these, and then you've got different connection schemes in there. Different size ball, Nippon Electric, D squared ball grid array, trademark, board on chip of Amcor, Micron Technologies, BOC they call it, chip pack, Mitsubishi, Kyocera. Kyocera is the high thermal coefficient of expansion ceramic, okay? Try to match things. So Kyocera basically ran the packaging business in the late 80s and the mid 90s. They had almost a monopoly on high-tech packages. Fujitsu, Amcor, flip chip technology, Sandia National Lab. Okay, form factor basically comes in here with some thermal compression bonds to some of these pads. However that works.
These are still level 2?
It's all still, well, it's chip to package, but it could be package to board, or it could be level 1 or 2. They basically use ball grid array on both levels 1 and 2. The smallest ones being for chip to package, and the larger ones being for board, as far as that goes. Okay? Any questions on any of that? So, anybody have any overall questions on, that's all I was going to talk about on microelectronic packaging, which is sort of an overview rather than, we will talk about soldering in printed circuit boards and stuff later.
Can you just go through the calculation you did yesterday about the 4-inch difference with 3 gigahertz and the speed of light?
The speed of light is 3 times 10 to the 8th meters per second, right? Remember that? Okay. And from somewhere back in your prior history, being a physicist or something. 3 gigahertz is 3 times 10 to the 9 hertz. Okay? Now hertz is per second. Okay? Now, I'm not enough of an electrical engineer to remember if I left out a 2 pi out of this or not. Okay? But who cares? Okay? There is a 1 over 2 pi in somewhere. Okay? So I might be off by a factor of 6. But in any case, that works out. I'm just dividing 10 to the 8th by 10 to the 9th. Okay? 10th of a meter. It's because the, I'm sorry, this is 3 times 10 to the minus 9 hertz, and that should be multiplying. Sorry. If that's what my problem was. It's 3 times 10 to the 8th meters per second. And the frequency of 3 times 10 to the minus 9 hertz, where hertz is per second, those cancel and I end up with 0.1 meters. Okay? That's the only thing. Meters is the only thing left, right? So, at this frequency, light only travels about a tenth of a meter.
In a second.
In a,
In a cycle.
in a cycle, in one cycle. So if I'm trying to use digital computation or something, at this frequency, each one of my bits can only travel 4 inches at the speed of light.
That's what it is.
Well, the bit is being transferred. The electron, and we don't actually have light unless we're doing fiber optics. Okay, and one of the advantages of fiber optics, we have no parasitic capacitance. But for electrons, the electron can travel at a maximum of the speed of light. Okay, so if the electron can only travel over this amount of time, then this is the distance it can travel in that time. Okay. Otherwise, it's coming back on the next cycle. Is that still lost?
No, I think I got it. Because you're not transferring data, you're having to do calculations. That's why.
You're moving electrons across that chip. I mean, the transistors, electrons going through the transistors, right?
Right, but you can move data at 3 gigahertz great distances.
You can move data, but you're doing it parallel to other
you
things.
can't do calculations.
You can't do the calculations on the chip.
Right, that's
Okay.
what was.
Yeah,
that
okay.
was-
Those little transistors have to switch on and off at this frequency. So I can't transfer the data 1 bit at a time from chip to chip at this kind of frequency. You actually can get higher frequencies than that. We know that because when you start doing parallel processing and stuff, but the point is we're getting down to the point where we have to start worrying about the distances that things travel. And again, I don't know that much about the parasitic capacitances. I know that this number is knocked down even more by parasitic capacitances. And I know that in the chip design, they are looking at, one of the big things now is how to reduce the capacitance. One of the big things is not to use aluminum oxide as the substrate material because it has a very high, it's a very strong insulator, very good insulator. And in fact, that increases the capacitance and it slows down the thing. If you could use aluminum nitride rather than aluminum oxide, okay, the aluminum oxide is an excellent insulator. And an excellent insulator gives you a very good capacitance. And I've got layers of metal and layers of ceramic, and I'm going to have capacitance in between there. Okay, that's what a capacitor is, right? It's 2 layers of metal with a sandwich of an insulator in between. With very good insulators, I get higher capacitance. Aluminum nitride actually has like 5 orders of magnitude higher conductivity. It's still an insulator, but it's 5 orders of magnitude higher conductivity, so the capacitance in the circuit is less. So people would love to build an aluminum nitride substrate rather than aluminum oxide substrate for these packaging substrates. I guess you've got it out there right now. Because they're getting limited by the parasitic capacitance. They call it parasitic because you're going to have these layers, sandwiches of conductors and non-conductors. And I'm just giving you the order of magnitude that we're getting down to the limits. This thing might be knocked down by a factor of 100 in terms of things, but yes, we do transfer data at higher rates. And we have computers that can compute at higher rates, but it's because they have to go to fancier substrates. They have to, it's all being done on the chip. Obviously 4 inches is huge compared to the chip. But depending on the substrates and everything else, there's other knockdown factors. That's the maximum speed at that frequency. If I'm at 30 gigahertz, my distance is 1/100th of a meter, which is a centimeter. Okay? I don't think we're going to find 30 gigahertz computers anytime soon, because if the chips are 1 centimeter, because this transistor can't talk to that transistor except at the speed of light. One of the reasons people would like to do fiber optic computing is there's no parasitic capacitance, which might knock you down by another factor of 10. Okay? But computing, transferring data off the board to something else, yeah, we do at tremendous speeds. A lot of that's fiber optics, okay? And those are even higher frequencies than this. Because fiber optics, we're talking about frequencies that are, infrared frequencies. So you're up by, what, 4 or 5 orders of magnitude. And that's why fiber optics can transfer so much data. So when you're doing really high-speed data transfer, it's all fiber optics. You try to do it over copper wire. In fact, that was, if Corning had not developed a cheap way to develop fiber optics, well, actually, back in the 1970s was when the U.S. Mint decided to switch from pure copper pennies to zinc pennies plated with copper. And the reason was, when the price of copper got to $1.60, it was going to be cheaper to melt your pennies down and sell them as copper than to sell them as a penny. They were worth more than a penny. Okay? And at that time, the price of copper was had fluctuated between 60 cents and like $1.20 in the 1970s. And the Mint realized that there are going to be a lot of people melting pennies down. And so that's why in the late 70s, they developed the zinc-based pennies. And zinc is at 40 cents a pound, had a long way to go, and there's plenty of zinc around. Well, today, copper is going for $2 a pound. So if we still had all those copper-based pennies out there, they would have been consumed by now. Okay? But the other problem was for intra-city communications, the copper cables were they were plugging up the streets of New York and stuff for the increased telephone usage and data transfer and everything else, because the copper cables really can't go much above, a few, gigahertz or whatever. When you want to go faster than that, you start using microwaves, which means you're using essentially radio waves in a conducting channel, right? It might be made out of copper, the tube, but it can be made out of stainless steel. You're using basically electromagnetic waves in the air inside the microwave channel to get very high data rates. Fiber optics came along, and I don't remember if it's 5 or 6 orders of magnitude faster frequency. And now we can have broadband and transfer data at tremendous rates, right? But getting it off the board is a big deal. In fact, about 10 years ago was when IBM announced that they had found a way to use copper as the conductor on a semiconductor chip. Before that, everybody had to use aluminum. And the reason they had to use aluminum next to the silicon is because aluminum doesn't poison the silicon. But copper will poison the silicon. If copper starts diffusing into the silicon, it destroys its semiconducting capacity. And so people wanted to use copper because of the higher electrical conductivity and the fact that this capacitance problem with the 60% or whatever higher conductivity of copper, you'd be able to run your chips much faster and much cooler. Okay? So IBM about 10 or 12 years ago announced they found a barrier layer. The magic barrier layer is titanium. But anyway, they patented it. And that's the PowerPC for you Macintosh fans or your gaming fans. The PowerPC was basically built around this copper-based technology that IBM came up with. Since then, IBM and other people have licensed it to other people. So most of the best performance chips today are based on copper, again, because you're running into these fundamental limitations of how fast things can go. You're limited by the electrical conductivity and the parasitic capacitance of these things on the chip. Okay, so that's because you're limited by metal conduction and electrons going through metals, and fiber optics and data transfer other ways is is other things. So when you put a fiber optic cable down, in fact, the first one went in New York City, it was about 2 miles long, and it took out supposedly a bundle of copper that was that big around. Okay, there's no more room in the manholes. Okay, they were having to get small people to go in the manholes to do the work. Okay, any other questions? No? See you Monday. 4 classes.